So hi everybody, my name is Davis Vaughan. I'm actually on the Tidy Models team at R Studio, but I am not here to talk to you about Tidy Models whatsoever. I'm here to talk to you about something very different, arrays in R. So in this talk, we're going to be needing some data. So we're going to pretend that we run a very successful candy store, and inside of that candy store, we've got this big bag of M&Ms. Inside of that bag, we have peanut and plain M&Ms, and we have M&Ms of different colors, green, red, and blue. This is a 2x3 matrix that just holds the counts of the different combinations of M&Ms that we have in that bag. This is mainly going to be a presentation of pictures rather than code because I find that a little bit easy to understand for these concepts. And to make it even easier and a little bit more fun, it's going to be colorful as well. So we are very successful in running our candy store, and M&M has taken notice and decided to give us some extra M&Ms just for free for doing a great job. Here we've got a 1x3 matrix of those extra M&Ms. Specifically, you've gotten 3 green peanut and 3 green plain M&Ms, 1 red peanut and 1 red plain M&M, 2 blue peanut and 2 blue plain M&Ms. Being the great shopkeep you are, you want to add those to your total number of counts to keep good records. So you might make that 1x3 matrix and kind of add it to your 2x3 matrix to get total counts. Do this with base R matrices, and obviously you'll get non-conformable arrays. So if you're wondering what's happening here and like, oh, I don't work with matrices that often, what's going on? With R, arithmetic between arrays and matrices are very strict. You have to have dimensions that are exactly the same. So having a 2x3 and 1x3 matrix, adding those together, that just won't work. You can do it with like a single vector or a vector that gets repeated. But when you move on to 2-dimensional or 3-dimensional structures, the actual dimensions have to match up exactly. I think there's actually an intuitive result here. And I think it looks a little bit like this. Here we have 15 added to 3 to get 18 in the top left, 10 plus 3 to get 13 in the bottom left, and you can kind of see that pattern repeated through the rest of the matrix. So the rest of this talk is going to be mainly focused on these ideas and a package that implements these ideas, and then a little bit on subsetting matrices as well. This idea is actually nothing new. If you're familiar with NumPy and Python, this is called broadcasting. So we'll get into that. So there's 3 things I'm going to be talking about. The last 2 there are somewhat related to broadcasting. The first one is on subsetting. So let's start with that. Here I've got my bag of M&Ms, and I might have said, you know what, I just care about the green and the red ones today. Give me that information. Immediately, you might do bracket, comma, 1, 2. That seems intuitive. You get the green and the red columns back. But I might say, oh, you know what, no, I changed my mind. Actually, I don't care about the red ones either. Just give me the green column back. So you might do comma 1, immediately expecting it to give you that green column. But you'll be slightly disappointed if you expected a matrix back, because it actually drops dimensions, and you end up with a vector instead. If you're kind of wondering, like, well, I mean, this is a little strange, what's going on here? The subsetting operator in base R has this drop equals true argument set. And what that does is anytime you see a dimension of size 1, it'll automatically drop it. So we went from a matrix that's 2-dimensional down to a vector that's 1D. You can easily fix this. Just set drop equals false. So now we've got our 1-column matrix that we expected, but this isn't an end-all solution, as you'll see in a moment. To kind of demonstrate this idea of why that's not an end-all solution, we're going to need to go 3-dimensional. But that's really nothing scary. Here, we just have 2 bags of M&Ms. On the top panel is the bag that we've been working with already. On the bottom panel is our second bag that just has new counts. It's still plain and peanut M&Ms, still green, red, and blue ones. I might ask you to kind of do the same thing we did on the previous page, where I just want that green column. Give me that somehow. You might fiddle around for a couple minutes and end up with something that looks like this, where you have comma 1, comma, comma, drop equals false. If you've ever done this before, this doesn't look that bad. but you might be interested by the fact that there's this extra comma here. When you're writing generic programming around arrays, this kind of thing can be slightly problematic. You want to be safe by always setting drop equals false, so you don't have the behavior where matrices are kind of dropped down to vectors or 3D arrays are dropped down to 2D matrices. But if you don't know the dimensionality of your input, it might be 3D, 2D, 4D, you have to kind of programmatically generate these commas, which might not be the most straightforward thing for beginners. Essentially, it involves generating this expression that you then have to kind of evaluate some other way. So what is the confusion here? My idea is that subsetting is not dimensionality stable, which is kind of a subset of this larger idea of not being type stable. What I mean there is that obviously you subset a 2D matrix and it could give you a 2D matrix back, or it could give you a 1D vector back. So this is where the package that I created comes into play. It's called RA. It's currently on GitHub. In the next coming weeks, it will be on CRAN. But RA is designed to provide a stricter array class, and it's also designed to provide this big toolkit around array manipulation. So creating an RA object is not hard. Here we've got our bag of M&Ms that we've been working with, 2x3 matrix. Call as RA on that, print it out, and you'll see that it essentially looks the same. It's just got a little bit of header information on top. But when you start subsetting these objects, you'll see that it works a little bit differently. In the top middle, we've just selected the first column like we did in our original example, but you'll notice that no dimensions have ever been dropped. It's still a 2D matrix. In the bottom middle, you'll see that 3D example we had before, where we wanted the first column of that. You just do comma 1, and no dimensions are ever dropped, and you extract your first column out. If you're a keen user of R and arrays especially, you'll notice something interesting. That bottom middle example of just comma 1 is actually an error with normal 3D arrays. You would have to specify comma 1 comma, and that would drop you from a 3D array down to a 2D matrix, but it would have the elements you see here. So that's all on subsetting. Hopefully that kind of piece it makes sense why I've done it this way. You'll see other things you can do with subsetting if you go look at all the documentation. I think it's rather neat. But for now, I'm going to move on to the topic of broadcasting. Broadcasting is this neat concept. It has to do with two things: increasing dimensionality, so going from 2-dimensional to 3-dimensional, and then recycling dimensions. Combining these two ideas together in a certain way allows you to actually perform kind of arithmetic operations or other types of operations between arrays of different dimensions. So where before we couldn't do that 2x3 matrix plus 1x3 matrix operation, broadcasting is going to provide us some rules to allow us to do that in kind of a stable way. So here's a modified version of that original example just to be a little bit more interesting. This is the 3D bags that we had before and our extra M&Ms that we were provided. Obviously, this gives us non-conformable arrays. If the other one did, this one probably does too. But I think even this has an intuitive result, and it kind of looks something like this. Here we have that extra matrix being kind of stretched and reshaped and duplicated in such a way that the dimensions match the 2x3x2 array of bags. With extra in this form, hopefully you can see how it's kind of element-wise added to bags to get the result you see on the right. So the next couple slides are going to be explaining how this happens and what broadcasting has to do with it. But what you should be thinking is how was extra reshaped so that this kind of manipulation was allowed to occur. When I explain broadcasting to people, I like to use this kind of table. On the left-hand side are our objects, bags, and extra. On the top are the dimensions, number of rows, number of columns, and just for a lack of a better term, for the third dimension, I've called it number of frames. In the actual elements are the dimensions there, so bags is 2x3x2, extra is 1x3. What you'll kind of immediately notice is that we have this gap here because we've left aligned the dimensions of extra and it's two-dimensional, not three-dimensional. So the first rule of broadcasting is that whenever you see these kind of implicit gaps, you have to add ones to match the dimensionality of the lower dimensionality objects, the 2D or extra matrix, up to the dimensionality of the higher dimensionality object, bags, which was 3D. So what does that all look like? If we go back to our picture here, in the top, here's our original extra matrix. In the bottom, here's the 3D version of it. It's just kind of been wrapped in that third dimension. So that's step one. Step two is that we have to go through each kind of column in this table and recycle dimensions, and then hopefully we'll be able to add these two things together. The way you do this is by looking down the rows. You'll see that bags has 2 rows, extra has 1 row, and anytime you see a 1, you can recycle it up to the size of the other kind of dimension. So here extra, it gets recycled from 1 row to 2 rows. Now both bags and extra will have 2 rows, so our output probably has 2 rows as well. What does that look like? Well, here you've got extra, our 3D version of it in the top, and here we just duplicate the row of extra down, and you can see that in just kind of this lighter shade of green, red, and blue. We'll just move on to the second column, or the second kind of column in our table, which matches the number of columns in our arrays. Not much to do here. Both of them have 3 columns, so our output probably also has 3 columns. Finally, we move on to the number of frames. It's the same thing as the number of rows in this case. Extra had 1, bags has 2, so we'll recycle the number of frames from 1 up to 2. Our output also has 2 frames, or 2 elements in the third dimension. What does that mean for extra? Well, we basically just took that entire panel in the third dimension, copied the whole thing down, and now we've got this duplicated version that's 2 by 3 by 2. We've now successfully broadcasted extra to the kind of common dimensions between bags and extra, and we can add them together to get the original result that I kind of talked about before. So this is a very flexible way that you can manipulate arrays of different dimensions, and there's really just 2 rules. The first is matching dimensionality by appending ones where it's missing, and then the second is matching the dimensions by recycling dimensions of size 1 up to the dimension of the other object. RA as a package and all throughout it broadcasts. So in arithmetic operations it does, but it also does in these other manipulation functions that you'll see in a moment. So if you just had bag and extra here and you tried to add them together, you'd get non-conformable arrays. But if either one of these was an RA object, or if you used the RA_add function with 2 base matrices, they would be added together in a way that broadcasts. The final section that I want to talk about is on manipulation of arrays. So RA is not just about this special new class. It doesn't just provide subsetting operations. It doesn't just provide new kind of arithmetic operations. It's this much larger toolkit with lots of functions inside for general manipulation of arrays. One in particular in the top left is RA bind. This is kind of a new cousin from rbind, cbind, and even from the abind package that's even more flexible than those 3 and allows you to bind things with broadcasting kind of baked in as well, which makes it extremely flexible. The neat thing is that all of these pieces in the toolkit work with base R2. I'm not trying to opt you in to force you to have to use this RA object to use anything in this package. Bring your own array, and all of these functions will work with it as well, and will return another base array or matrix. So in the bottom left, you'll see RA sum, and for my final example, that's the function I'll be using. What we're going to do is look back at bags one last time and say, we want to compute some proportions here. First, we're going to kind of sum up the total counts and do an overall proportion just by dividing by that total number. Then we're going to do it row-wise by kind of filling peanut or plain. And then we're going to do it by column, doing it by color. This is how one way that you might kind of do this with traditional R. You might do bag divided by the sum of bag to get the overall proportions. And then you might venture into this land of sweep and apply, using apply to get the sums, and then sweep to do the kind of row-wise division. If you wanted to do it by column instead, you'll just switch out that margin argument from 1 to 2, and that's how you'll get column-wise proportions. With RA, the way that RA sum works in combination with the broadcasting from the division operator makes it as simple as this. Here we've got bag divided by RA sum with no axis argument. That just means take a global sum. Broadcasting kicks in and makes the division work correctly. Same thing with the row-wise version. It does look backwards from before, where we have axis set to 2 and margin was set to 1, but that is on purpose. That's the way axes work, and that's all written up in the vignette describing the difference. But the neat thing here is that because of what RA sum returns in the middle example, which is a 2-by-1 matrix, that can be broadcast against the original bag in the division to make things work as expected. So in conclusion, RA is a stricter array class. It provides this neat broadcasting idea to make things a bit more flexible and more fun. And then it's got this big toolkit for general array manipulation. I'll leave you with this tweet here where someone found RA early on and implemented this kind of neat neural network inside of it. I have no idea how he did this because it was totally broken at the time. And then he's got this nice tweet at the bottom just saying that he really enjoys RA. I have to give a plug to QuantStack. They are the ones that have written Xtensor, this C++ header library, which provides the actual speed and performance behind the RA package. Thank you.
Thank you. We have time for one question. There's already, sorry. You can ask in the coffee break.
Okay, thank you for the presentation. If I understood correctly, the new array object is designed for three-dimensional arrays. And yeah or not? Or
It's n-dimensional. An Xtensor is like an n-dimensional library, so it works for any dimension.
Okay, so for example, when we have this syntax with one comma omitted for subsetting, how does it work, for example, for four-dimensional arrays?
Did you see the one with like the 3 dimensions there, and it pulled out the first column and kept all the other dimensions? So it'll work the same way.
Ah, okay.
So it'll,
okay,
yeah.
Thank you.
It assumes that if you do comma 1, you want the first element in the second dimension. You want to keep all the elements in all the other dimensions.